Alright, welcome. In this video I'm going to be working some slope field examples. Specifically I'm going to be working through BC Homework 5.1. Alright, so it's going to start with, a very typical slope field thing. Here's some dots, color in a slope field. Alright, so on the axes provided, sketch a slope field for dy dx equals y minus 2x at the 8 indicated points. Okay, so I'm going to come in, I'm going to make a little table, but then I'm probably not going to want that to work around forever, so I'm just going to use a little post-it note here. So I'm going to make a table x, y, and dy dx. Okay, I'm going to fill in the coordinates of the points I'm interested in finding the slope at, and then I'm going to fill in the corresponding slope for each coordinate pair. I did y minus 2x, and just did that, while it was paused, save a little time on the video. And so now I'm going to go in and I'm going to color, a slope of 0 at x equals 0 and y equals 0. Okay, so the slope field's a little small, so I'm going to try to get it all in the shot. All right, so at the origin, it's slope 0. At 0, negative 1, the slope is negative 1. At 0, 1, the slope is positive 1. And at 0, 2, the slope is positive 2. Okay, so don't really have anything to aim at, so I just make sure it's steeper than that one. Okay, and then at 1, 0, the slope is going to be negative 2, so that's pretty steep. At 1, negative 1, it's negative 3, so that's, even steeper. At 1, 1, the slope is negative 1, so about like that. And at 1, 2, the slope is 0. So we give it a little slope field like that. And this is probably the most typical of the slope field problems that you would see on a free response section in an AP exam. It's just like, here's a little bit, give me a little bit of the slope field. Okay. Second part is going to be, I'm not sure, look at it. Find the second derivative. Okay, we can definitely do that. All right, so the second derivative is going to be equal to the derivative of this thing with respect to x. So the derivative of y with respect to x is dy dx minus the derivative of 2x with respect to x is 2. Okay, but it said in terms of x and y only, so we need to substitute back on dy dx. dy dx is y minus 2x, so this is y minus 2x minus 2. So let f be the particular solution to the differential equation that goes through the point 1, 2. So it goes through that point. Okay, does f have a relative maximum, a relative minimum, or neither at the point 1, 2, and give a reason for my answer? Well, the thing is that I already know that dy dx is 0 at this point. So I'm going to say, well, at 1, 2, dy dx equals 0, and the second derivative is equal to dy dx minus 2, so that's going to be 0 minus 2, which is negative. So I'm going to conclude that because the derivative is 0 and the second derivative is negative, the graph is flat while being concave down, meaning we've got a relative maximum. And that's a pretty typical free response question. There might be another part in it, as you know, that maybe a multilinear approximation or something like that. But this is pretty typical for a non-separable differential equation. You don't really know what that means yet, but eventually we're going to be able to take some of these and solve them for y. But this is not going to be one of them that we'll have in this class. All right, so this one, we're going to do the exact same thing. We're going to sketch a slope field for the given differential equation at the 9 indicated points. Okay, so I'm going to do the same thing. All right, I'm going to have to write pretty small. So x can be 0, 1, or 2, and y can also be 0, 1, or 2. So yep, it's still visible. My shot, 0, 1, 2, 0, 1, 2, 0, 1, 2. And now dy dx is going to be y squared divided by x minus 1. All right, so y squared is going to be 0 in this case, so that will be... Why would I have you do this at a place where I'm going to be dividing by 0? Let's see. That looks troublesome. Okay, yeah, this is the thing that I think I told you in class would not happen, right? They won't ask you, okay, so 0, 0. 0 divided by negative 1 is definitely 0. We'll put in a flat tangent there. Okay, 1 divided by 0 minus 1, that's going to be negative 1. So these will be all right. These ones where x is 0, I can do those fine. Slope of negative 1, x is 2, y squared is 4, divided by negative 1, that's going to be negative 4. That's just extremely steep and negative. Okay, so maybe something like that. Okay, when x is 1 and y is 0, then you have 0 divided by 0, and we don't know what to make of that. That will never happen again. Okay. When y is 1 and x is 1, I have 1 divided by 0, and that's something we saw in the last unit, evidence of a vertical tangent. So I'm going to just put in a little vertical tick mark there. But I wouldn't ask you to do that on the quiz or the test, because if you said, okay, dy dx doesn't exist here, so there is no tangent line, I would probably be all right with that. Where y is 2 and x is 1, you're going to have 4 divided by 0, and that's, again, going to be a vertical tangent. Okay, where x is 2 and y is 0, I'm going to have a slope of 0. Okay, make sure that's flat. Where y is 1 and x is 2, I'm going to have 1 squared over 2 minus 1, that's 1. And then when x is 2 and y is 2, I'm going to have 4 over 1 is going to be 4. So I'm going to try to make it about as steep as that, but positive. And there we've got ourselves a slope field. Okay. But this whole thing here, this probably shouldn't be happening in the future. So let y equals g of x be the particular solution to dy dx is y squared over x minus 1 with the initial condition g of 2 equals 2. Write an equation for the tangent line to the graph of g at the point 2, 2. All right, well, we determined that at the point 2, 2, just use the work we already did, dy dx equals 4. Okay, so dy dx equals 4. The point is going to be 2, 2. So the equation is going to be y minus 2 is equal to 4 times x minus 2. Then we're going to find the second derivative. And then we're going to plug in 2, 2 after that. Okay, the second derivative. We're going to need to use the quotient rule because the first derivative is a quotient. So the second derivative of y with respect to x both times is going to be equal to bottom derivative of top. Okay, and I'm just going to leave dy dx right there because I already know dy dx is the point I'm interested in is going to be 4. So I don't need to go back in and substitute that fraction over here and do that same computation again. That would just be a waste of time. Minus the top times the derivative of the bottom. That's going to be 1 divided by the bottom squared. That's x minus 1 squared. Now I'm going to plug in 2, 2. That's going to be 2 minus 1 is 1, 2y is 4, dy dx is also 4, minus y squared is looking like 4, divided by 2 minus 1 squared is just going to be another 1, and that's going to be 12. Okay. And then when it asks if the tangent line I wrote in part B is above or below the graph of g, I'm going to say because the second derivative is positive, the tangent sits below the curve, right? It's smiling, it's got a slope of 4, something like that. Doesn't really matter what the slope is. If it's smiling, if it's concave up, second derivative is positive, the tangent sits below the curve. All right, and that's all we got for that. All right, next we've got another differential equation, but this is one where they're going to give you the slope field already produced. And then you probably know what's going to happen after that. You're going to have to color in a solution curve and hopefully stay in the lines. So sketch the particular solution to the differential equation that passes through the point 0, 2. Okay, that's this one. Okay, here at 0, 2, let's look a little closer at this. Yeah, that's better. At 0, 2, you can see that it's just like a bunch of flat lines through here. So I'm going to say the solution curve is just this horizontal line. Right? But then at the point 1, 0, that's right here, I can see that generally it's kind of doing, it's like a kind of a curve situation. And so I know that, you know, there it's going to go like that. And we're just going to go down and back up like that. And remember that kind of the standard is that our curve needs to extend to the edges of the window, right, to the edge of the slope field. And there just needs to not be any flagrant contradictions with the slope field. And if you look, you know, like it's not perfect here, you know, the slopes aren't exactly what the slope field is saying, but there's no flagrant contradiction, right? There's no place where my curve is like perpendicular to the slope field or like just going in the complete opposite direction or anything like that. So this is going to be suitable curves. I don't exactly recall how zoomed in I was at the beginning, but I guess I was zoomed enough to get the whole problem visible. All right, this looks good. Find the second derivative in terms of x and y only. Okay, this is a product, so I'm going to need to observe the product rule. So take the derivative of the first factor, the derivative of 1/3 of x with respect to x is just 1/3, leave the y minus 2 squared the same. Then add in, leaving 1/3 x the same, the derivative of y minus 2 squared. Okay, so this is like this has got layers to it, right? On the outside we've got the squaring, on the inside we've got y minus 2, and y minus 2 is going to have its own derivative with respect to x. It'll just be dy dx minus 0. But, okay, so I'm going to say 2 times that thing to the first times the derivative of that thing. All right, and then I need to find it in terms of x and y only, so I'm going to just replace dy dx with a 1/3 x y minus 2 squared. Okay, plus 1/3 x times 2 times y minus 2 times dy dx is 1/3 x times y minus 2 squared. And if you wanted to, you could certainly like combine these, make 3 powers of y minus 2. And combine the 1/3 x and the 1/3 x and make 1/9 of x squared. You could even factor out 2 copies and maybe even the third and, you know, have a factored version of the second derivative. But it'd be no more correct than this one. And when I go to do this whole consideration that 0, -4 is it a max, min, or neither, I'm going to go straight to that one because hopefully I'll have dy dx first because I need to check and see if dy dx is equal to 0. Because I know you know that if I plug in the point 0, -4 into dy dx and I don't get 0, then it's going to be neither a max nor a min because it'll be in the midst of increasing or the midst of decreasing depending on the sign of dy dx. But it looks to me because of the 1/3 x and the x being 0 that dy dx is going to equal 0. -4 minus -6 squared. Doesn't matter. That's 0. The whole product is going to be 0. Okay, the second derivative at that point is going to be, I'm going to go, and I'm going to use this formula right here. 1/3 of y minus 2 squared is 1/3 of -6 squared plus 1/3 of x, plus a bunch of stuff that's all, oh, you can't see that, but it's a bunch of stuff that's all multiplied together and has a dy dx in it, and I just showed that dy dx is 0, so this whole term is going to go to 0. So I'm just going to say plus 0. Okay, that's 36 divided by 3 is 12. Okay. So as a result, I'm going to say that, okay, since the derivative is 0 and the second derivative is positive, I'm sitting at a relative minimum. And remember that my reason is this work right here, not that. Okay, that's just to remind me that flat while concave up is going to be a minimum and not a maximum. All right, shown below is the slope field for the differential equation. We're going to sketch a solution curve. We are going to write an equation for the tangent line and use it to approximate a function. So really we're just, you know, mixing in some slope field discussion, but continuing to practice the stuff that we did in the last unit. And I think you'll see that throughout this unit. Okay, let's just look more closely. All right, It says the point x is 0, y is 1. So it's going to be this one. And looks to me like it's kind of going kind of down, up, down. So, I mean, this is pretty small, but all right, doesn't look very contradictory, but not sure what I would do if it did, because I'm going in pen. Okay, just kind of follow the lay of the land, extend to the edge of the viewing window. You can give it arrows at the edge, or you cannot give it arrows at the edge, whatever you feel like, just as long as we're going all the way to the edge. We're just generally following the pattern that we see with the slope field. Not trying to be too perfect. And there we go. All right, so let G be the particular solution. Write an equation for the line tangent to the graph of G at the point 0, 1. All right, well, the point is 0, 1. The slope is going to be dy dx equals, okay, 3 minus y is 2 times the cosine of x, and the cosine of 0 is 1, so that's going to be 2. And that looks, I don't know, kind of believable. Maybe didn't make it steep enough right at the beginning, but, you know, again, it's following the general patterns. It's going to be all right. So the equation is going to be y minus 1 is equal to 2 times x minus 0. And then use the tangent line I just wrote to estimate the value of g of negative 0.03. So I'm going to add that 1 over here, add 2 times negative 0.03 minus 0 is just... So 1 minus 6 cents is going to be 94 cents. Okay, find the second derivative. Okay, we're going to need to start by taking the derivative of this with respect to x. So the derivative of 3 minus y is going to be 0 minus the derivative of y with respect to x, so negative dy dx. Okay, and then I'll leave cosine x the same. Then I'm going to add n, leaving the 3 minus y the same, taking the derivative of cosine x with respect to x, and that's going to be negative sine x. Okay. And then, wait, I just found dy dx, that was 2, and we're still talking about the same point, 0, 1. Okay, so I'm just going to use dy dx equals 2, right? Because it didn't say find the second derivative in terms of x and y only. So I'm going to say negative dy dx was 2, cosine of x was cosine of 0, that's 1, plus, okay, 3 minus y is 2, and negative sine of x at x equals 0, okay, well, sine of 0 is 0. All right, so that's equal to negative 2. And then, is my estimation greater than or less than the true value of g of negative 0.03? Give a reason for my answer. Well, I know that the second derivative is negative, and that's pretty much the entire consideration. And, you know, maybe the tangent line I wrote was like that. The estimate that I got was, you know, to the left of the centering point. But because the second derivative is negative, it didn't matter if I was to the left or the right. The value on the line is greater than the value on the curve, so the estimation is greater than the true value. Okay, so at the point 0, 1, the second derivative is negative. That's why I'm concluding what I'm concluding. All right, now some slope field matching. And that's pretty typical. That's a very common multiple choice question. Is here's a differential equation, which of these is a slope field? I think I spiced this one up a little bit by, you know, giving you 3 of them and having you find the 4th, right? That's just something different. Okay, so what's going on here? I am not sure on A if those things along the y-axis are horizontal tick marks or just actually, you know, like the scale on the y-axis. I don't know. I tend to think, based on the overall behavior of the graph, that it's just the tick marks, that we would actually be seeing vertical tangents there. Okay, so, but I'm not entirely sure. Oh, yeah, I am pretty sure, because I think that's going to be the one with no match. Okay, so e to the negative 2x. I'm going to start with that one. I'm going to try to identify based on the equation, not go the other way. Because I got trig over here. I think that these are both going to be the trig, because they're kind of wavy. This one, who knows? But the thing about e to the negative 2x is that e to the negative 2x is positive for any x. And so I need to look and find one that has no negative slopes anywhere. And I'm seeing negative slopes on this one, and this one, and this one, so D must be e to the negative 2x. Okay. 1/2 sine of x. Okay, so these slopes are going to have to be pretty small, because I know that sine of x is kind of stuck between -1 and 1. And specifically, I know that sine of 0 is equal to 0, so I need dy dx to equal 0 when x is equal to 0, and that is not what I'm seeing right here. So I see flat slopes here at where x is equal to 0 along the y-axis, and so I'm going to conclude that c goes with 1/2 sine x. Okay. So I think that's going to mean this one's going to need to be cosine of 2x, and so let's think about what happens at 0, right? That's going to be a pretty good way to go. So where x is equal to 0, I'm seeing cosine of 0 equals 1, so I should be seeing slope of 1. That looks believable to me as like a slope of 1. So I'm going to say that's B. And then for dy dx equals this one, what's going on here? It looks like the closer I'm getting to the y-axis, the steeper my slopes are getting. And I've got it negative over here and positive over here. So I think the dy dx equals 1 over x is going to kind of fit that pattern. And I think that's also, we looked at that slope field once in the lesson, and I remember it looked very similar. It looked like the solution curves were looking like the graph of, log of x or something like that. Okay. All right, sketch the slope field for dy dx is negative x plus 1. Sketch the solution curve that passes through 2, 1. Okay, that's not something I would ask you to do on the quiz or the test or anything, because it's like, if you mess up the slope field, then your curve's going to be really bad. Wouldn't ask you to do it on the AP exam either. They either ask you to sketch the slope field or to sketch the solution curve, but not both. But we can do this, right? So let's start with x equals 1, then dy dx equals 0. So since dy dx only depends on x, I'm going to only make a dy dx versus x chart. So when x is -1, dy dx is -2, x is 0, y is, wait a second. No, that's going to be positive 2. Okay. When x is 0, dy dx is going to be 1. When x is 1, -1 plus 1 is 0. 2 and 3. -2 plus 1 is -1. -3 plus 1 is -2. All right. So at x equals 1, we've got 0 slopes. Whoops, it's supposed to be horizontal. Okay. At x equals 0, dy dx is 1, so that's a pretty easy slope to draw. I'm just kind of aiming up at the next grid intersection point. And no, I was aiming down at the previous grid intersection point. All right, and then when x equals -1, dy dx is -2, so, or positive 2. So I'm going to start here, and I'm going to be aiming for that, and okay, and then once I don't have anything to aim for, I just kind of try to make them parallel, right? Just do the best you can. Okay, where x is equal to 2, dy dx is -1. And where x is equal to 3, dy dx is -2. All right. Is emerging. But I think you could probably, if you thought really, really hard about it, you could kind of reverse engineer a function that would have derivative dy dx equals -x plus 1. And well, that might mean something to you. Okay, but we're going to sketch the solution curve that passes through the point 2, 1. Maybe orange wasn't the best choice. That was pretty rough. But, you know, it didn't have any flagrant contradictions to this slope field. We extend it to the edges. That's what really matters here. All right. Okay, now we're going to do the exact same thing here. And that's kind of a lot of points to be sketching a slope field for something that doesn't, you know, that depends on both x and y, but, you know, we can do it. All right. So I'm going to kind of speed this up. All right, we're going to have to take some sort of strategy because there's like 20 points on here, and that's just going to be too much to make a table, right? So let's think about where y equals 2x, the slope is going to be 0. So that's here, and that's seriously going to be it. Okay, that's a little annoying. Okay, well, that's 2 of them with one. So let's talk about where x is equal to 0. If x is equal to 0, y prime is just equal to y. Okay, so x equals 0 here, y was 0, the slope was 0. Y is 1, the slope is going to be 1. Y is 2, the slope is going to be 2. And y is 3, the slope is going to be 3. Y is 1, slope negative 1. Okay. If y is 0, then dy dx is going to be negative 2x. All right, so negative 2 times negative 1, that's going to be positive 2. All right, and then at negative 2 times 1 is going to be negative 2. And then negative 2 times positive 2 will be negative 4, which is just really steep. Whoops. All right. Then at, just like, there's not going to be enough room over here for me to fill in all 20 of the points. Okay, at 1, 1, I'll have 1 minus 2 is negative 1. Okay. At 2, 1, that'll be 1 minus 4 is negative 3, so that's still really steep. What to aim for. All right. Y minus 2x is negative 1, minus 4 is negative 5, that might as well be vertical. Okay. Over here, where x is 1 and y is negative 1 minus 2 is negative 3, so I'm aiming for that one. This one's kind of a mess. Negative 1 is negative 1 plus 2 is positive 1. And right, negative 1 is 1 plus 2 is 3. That's very steep. And let's see, negative 1, 2. 2 plus 2 is 4. Okay, just more or less vertical, but just with a little bit of positive slope. And then this one, I mean, plus 3 plus 2 is slope of 5, so even more vertical. Kind of tough to draw those where the slope is 4 or 5. Right, doesn't make that much sense. Then 1, 3. So it's 3 minus 2 is 1. Oh, that's nice. Okay, 2 is going to be 2 minus 4 is negative 2. And 3 is going to be 2 minus 6 is negative 4. I think that's, sure there's a tick mark in there. I did a wrong calculation. I had to do it quick. So I think what's going to happen here, it's not that much slope field to go off of, but if I had to make a guess, well, I know it's going to be, you know, the slope's going to be kind of like that at first. And it looks like it's getting steeper, so I could say maybe it's going to go like that. I probably should have gotten a little more steep, but that's going to be good enough. Okay, but I know that by the time I go back over here, it's going to have negative slope, so I got to have some sort of, maximum there. And I think that's about all I can say for that curve. All right. Okay, I remember this question. I don't remember what the kind of the punchline is. Okay, could a solution to the differential equation have the graph shown below explain? Well, let's think. I think it has something to do with the concavity. Let's see. Let me investigate that. Let's take the second derivative. think that what you'll find is that it is positive, like it's going to have a 0 slope at the origin, but I think it might be supposed to be concave down. I don't know. All right, second derivative, that's equal to take the derivative of x, leave y the same, or y minus 1 squared the same. Then leave x the same and take the derivative of that. That's going to be 2 times y minus 1 to the first times dy dx. Okay, and so all right, if I combine all of these things, 2x and another dy dx, that'll be 2x squared. I'll bring in 2 more powers of y minus 1, so that'll be y minus 1 to the third. And so that will be, I'm going to factor out 2 powers of y minus 1 squared, or wait, just 2 powers of y minus 1. Now I'll be left with a 1 plus 2x squared times y minus 1. And let's see, at the place where, at the origin, I should have 1 times 1 plus 0. Okay. That would be a 1 second derivative. It looks believable. I'm going to go look at the solutions I wrote up last year. Interesting. It says no. My key says no and find your own explanation. So hold on a second. I see something, and it was much easier than taking the second derivative. All right, so I'm saying that any place where y equals 1, dy dx equals 0, right? Okay, because if I had 1 here, that would be something times 0. Yet I'm not seeing a flat tangent there, or there for that matter. Okay, and although I am seeing a flat tangent where x is equal to 0, we'd have all of these. We'd also have these being kind of like flat spots on the slope field. So we can't have a solution curve so flagrantly contradicting the slope field, right? Okay, so that's, I think that's the best reason, is that at y equals 1, the slope needs to be horizontal. I'm sure there's another reason, and if you've got another reason, please bring it to me in class next time. I'd be curious. I don't want to sit here and look at this too long, but not really seeing anything else. All right. The last page, here we go. Write an equation for the slope field pictured. This is significantly more challenging than what you're asked to do with slope fields on the AP exam, right? It's really just sketch the slope field, sketch the solution curve, and match them up. But, because of the homework, I'll ask you the challenging question. So all slopes in quadrant 1 are negative. I think that's going to be something I'm going to use to check my answer at the end. The derivative at 1, 1 is negative 0.2, and dy dx at negative 5 and positive 2 is equal to 2. So I can see that any time that x is equal to 0, or y is equal to 0, dy dx is equal to 0. So that's going to be a huge hint. I think it's going to be some number times x times y. And I think that just as long as that number k is a negative number, that will take care of quadrant 1 having negative slopes, right? Because x and y are both positive in quadrant 1. If k is negative, that'll take care of it. So hopefully I can, fill this in and, solve a little nonlinear system to find the value of k. So dy dx at 1, 1 is negative 0.2. K times 1 times 1. Could it be that easy? Could it be that k is negative 0.2? All right, let's test it against the thing about negative 5 and 2. So does 2 equal negative 0.2 times negative 5 times 2? Well, that's negative 10 times negative 0.2 is going to be positive 2. Okay, so I feel good about this, and this is going to be all the slopes in quadrant 1 are negative. So my differential equation is equal to negative 0.2 times x times y. But that's the type of thing that, you're not going to be confronted with on the quiz or the test or anything like that. That was just a more interesting problem. Then show that a plus ce to the kt is a solution to the differential equation dy dt is k times y minus a. Okay. Not really sure how what this has to do with slope fields, but I think it has to do with what we're going to be doing, over the next couple of classes. So showing that something is a solution to a differential equation is, I'm going to take the derivative with respect to t here, and hopefully get something equivalent to that back, right? So dy dt is equal to the derivative of a with respect to t is going to be 0. Because I am assuming that a and c are constants. I don't think, it doesn't say it, but I know that that's what it means. So is equal to 0 plus the derivative of a number times e to the number times t is just going to be that same thing, times k for the chain rule. Okay. Now, I'm going to also ask you to notice that y minus a is equal to y subtract a is going to be c to the kt. So what I have is dy dt equaling k times that y minus a, that's c to the kt. Okay. Which is what I'd set out to show in the first place. And I think that's all, but I do have a set of a couple more problems, like a slope field multiple choice quiz, and I think I'm just going to do that on this video, so I'm just going to go grab that piece of paper. All right, yeah, so I've probably got this listed on as it's like 5.1 extra practice, and I'm just going to do it right now because it's only 3 problems. Okay. Which function could be a particular solution to the differential equation whose slope field is shown below? And so these are curves that would fit in with the slope field. So obviously we're going to need something that is increasing always, because it's always got positive slope, and kind of levels off. Okay, so square root, natural log, things like that. X squared, that looks like that. It's got the wrong concavity, right? Y equals x squared is very happy. It's concave up. These solutions are clearly concave down. E to the x, same story, right? E to the x is very concave up. E to the negative x is exponential decay. It goes towards 0. Again, it's still concave up, so, it's not really fitting. Cosine, we know it goes up and down, and this is only going up. So that's why it's got to be E. And, we know that the graph of y equals natural log x looks like that. It's got a vertical asymptote at x equals 0. Its x-intercept is x equals 1, and it increases for all x, because to get a bigger value of e to the x, you have to put on a bigger value of x. It's really the mechanism at play there. All right, which differential equation describes my slope field right here? We have some experience with this one. I think this one's on the note packets. So this one is when x equals -1, that gives me slope 0. Okay, but also here, when y equals 0, that's giving me y prime equals 0. Okay, so this does not depend on y, and you can see that as I go up and down on, say, that column of slopes, I'm getting different slopes. So my equation has to depend on x, or on at least y, right? I could do the same consideration with maybe this first row above the x-axis and see that it's going to need to depend on both x and y. All right. So when y equals 0, I need a guarantee that y prime is equal to 0. That's not going to work, because if y prime is equal to 0, dy dx equals x. And that's not guaranteed 0, right? This one, possibly. This one, possibly. This one, possibly. Okay, so I was able to, hold on. The blue condition is that y equals 0 guarantees slope 0. So that one's out based on that. I'm going to need like green or something. Find the green pen. Oh, no, this one's running out, but it'll be all right. Then from there, we need, if x equals -1, y prime has to be 0. So if x equals -1, dy dx equals -y, and answer choice A. That's not guaranteed 0, so that's not going to get the job done for me. And then basically if you plug in x equals -1, here you're going to get -y plus y, which is guaranteed to be 0, regardless of what y is. So I'm going to say that answer choice C is the winner. Okay. And the reason this one wouldn't work is that, you know, if you plugged in -1 for x, you'd get -2y, which is not always 0, right? You need y equals 0 for that to be true. And the last one here, which is the following, is the slope field for the differential equation dy dx is y squared minus 1. Let's see. All right. I always like to go based on 0 slopes. I feel like that's the easiest thing to see on a slope field. It's the easiest thing to pull out of a differential equation. So let's just think about what's going to make dy dx equals 0. That's where y squared minus 1 equals 0. I can factor. You can't see it, but I factored. And then I say this happens when y is equal to 1 or when y is equal to -1. So I need to have two places where I'm seeing horizontal tangents. That's going to be important. And so I think that's right here. That's right here on answer choice A, right? I'm seeing it's not exactly horizontal, but I know that it went from negative to positive as I kind of moved down on y, and it went from negative to positive as I moved up on y. So I feel like that's, you know, generally pretty good indicator that got 0 slopes happening in there. And for these, I'm not seeing 0 slopes happen at -1 and 1 at all, right? This is just not happening. Okay, it's happening on the y-axis, but not over here, right? I would need at y equals 1 and y equals -1 to be seeing horizontality. And over here, same thing, you know, I'm seeing them over here, but this is trig somehow, right? You can see it's going to be trig and x. Moreover, you could probably have eliminated based on the fact that these things need to depend on y only, so as you move side to side, we can't be seeing different slopes. Yeah, I'm going to actually say a little more about that. So if it depends on y only, as I manipulate x, I shouldn't be seeing different slopes, right? Which is the case for E, but is not the case here, right? I'm seeing a variety of slopes. This one too. Variety of slopes, variety of slopes. Okay, so we can eliminate all 3 of these based on the fact that my differential equation depends on y only. And that's really all I've got for you for this video.